Welcome to this video on the paradigm shift in next-generation air mobility. We will be exploring the ecosystem as of July 2026, analyzing developments across policy, defense, hardware, and infrastructure. This video examines how isolated hardware is transitioning into an integrated societal infrastructure. We'll cover key areas: policy bifurcation, cyber-physical acceleration, and the emergence of a 3D infrastructure grid. In July 2026, Japan implemented a dual-track regulatory environment. This approach balances strict national security measures, such as flight restrictions near critical infrastructure, with aggressive deregulation aimed at industrial liberation and automation. These new regulations introduce clear security perimeters. Overflight of red zones now carries significant penalties, including potential imprisonment or heavy fines. Yellow zones also mandate strict compliance, with no prior warnings required for unauthorized flights. Conversely, exclusive industrial zones have achieved complete regulatory exemption. This shift allows for instant, on-demand anomaly inspections using drones, bypassing previous permit requirements that hindered rapid responses to equipment failures. Global defense strategy is also evolving as unmanned systems become a foundational element. We are seeing major budget reallocations toward counter-drone capabilities, with tactical drone frameworks now playing a key role in international diplomacy. NATO has signaled this shift with a historic $40 billion commitment to the Drone Edge initiative. This 5-year investment focuses on advanced counter-drone capabilities, standardized procurement, and a significant expansion of trained drone operators. Ukraine is leveraging its real-world combat data to forge new diplomatic and strategic agreements. By sharing intelligence on countering drone threats, they have established partnerships with multiple nations to accelerate joint weapon production. Allied forces are successfully integrating autonomous capabilities into legacy platforms. Projects like Australia's Aladdin supply drone and the UK's Neon strike drone demonstrate how this technology sustains logistics and maritime strike power in contested environments. Counter-drone technology is now critical for civilian infrastructure. During the 2026 FIFA World Cup, massive security operations were deployed to manage airspace incursions, highlighting the necessity of integrated mitigation teams for public events. Technological advancements are pushing hardware beyond human endurance. New systems are designed for extreme climate tolerance, reliable beyond visual line-of-sight operations, and automated, unattended docking infrastructure, reducing the need for constant on-site personnel. Hardware capability is reaching new heights, from ozone sampling at the summit of Mount Everest to crevasse detection and logistics in extreme cold. Drones are replacing traditional methods to achieve safer and more efficient data collection. The realization of Type 2 certification marks a milestone for fully uncrewed operations. This allows certified operators to manage complex flights, including overpopulated areas, remotely, shifting the operational model to centralized management. Safety standards are also evolving. Automated parachute systems have become a standard feature, providing a critical safety layer that enables compliant urban infrastructure operations by ensuring controlled descents in the event of failure. Finally, we are entering the cyber-physical era. Digital twins now ingest real-time sensor data to simulate countless scenarios, allowing for optimized, risk-free routing to be fed back to physical drones for flawless, automated execution. Moving to real-world applications, we see how digital twins are closing the loop. Drones capture initial spatial data, which is integrated into the Providence platform. This creates a high-fidelity virtual replica, allowing AI to simulate physics and map safe routes before the physical drone ever launches. AI simulators are shifting strategy from reaction to prediction. By modeling complex scenarios, such as flood paths during storms, avalanche risks for infrastructure, reservoir depletion, or even kinetic ground impacts, organizations can plan for and mitigate crises before they fully materialize. We are also unlocking the subterranean frontier. Aging sewer infrastructure, previously dangerous for human inspection due to toxic gases, is now being mapped by microdrones. This partnership between robotics and GIS cuts inspection time by 60% and completely eliminates human risk. The next step is scaling to human transport through advanced air mobility. With hundreds of successful test flights and new vertiport infrastructure being built in major travel hubs, these systems are transforming high-traffic destinations into functional 3D mobility centers by 2026. Finally, the race for a 3D telecom grid is underway in the stratosphere. Companies are deploying lighter-than-air blimps to provide continuous broadband and disaster recovery, while defense initiatives are engineering these networks to remain resilient against jamming and electronic warfare. Thank you for watching this overview of the 2026 cyber-physical grid. From simulation to subterranean and stratospheric operations, these integrated technologies are fundamentally reshaping our infrastructure and mobility landscape.